Hello everyone, this video is going to cover sections 4.1 and 4.2 from the book. Now we're going to use the derivatives to find maximums and minimums. You actually did something similar in algebra, but it was very limited. In algebra, this is what you usually do, either intermediate or college algebra. You have a parabola, and then they ask you to find the maximum, and what you do, you find the vertex. There is two formulas to find the vertex, and once you find the vertex, then this will be the max, and that's pretty much what you do in algebra, either college or intermediate algebra. So now we're gonna expand this knowledge you have before. We're gonna add calculus. The goal is still to find either the maximum or the minimum values, but now we're gonna have more interested or complicated functions than just quadratic equations. The idea is actually very simple. You already know how to find the derivative of many functions, and remember the derivative is nothing more than the slope. So as you can see here, the slope is increasing, and then it gets to a point where the slope is 0. So this is going to be the goal, to find where the slope is 0. You can see that at this point, clearly this is the maximum, and that will happen when the slope, or in our case, the derivative is 0, and then it decreases. Okay? The difference now is that we don't have to only solve or limit ourselves to solve quadratic equations. Now we can do any function or any continuous function. For example, you can have something that looks like this. Okay? And you can see here the slope is increasing, gets to a point where it's 0, decreases, and so forth. So this point, and this point, and this point will be maximums or minimums. So a little bit of terminology. This one is considered a relative maximum. This is also a relative maximum, or sometimes they are just called local maximum. And this is a relative minimum. So as you can see, you can have more than one relative maximum and a relative minimum. However, there is also something called an absolute maximum and absolute minimum. For that, you have to restrict the domain usually. So let's say you only go from here to, let's say, here. So let's say this is A and this is B. So you can see that not only this is a relative maximum, now it will be the absolute maximum, and this will be the absolute minimum. Now these two values don't have to be the same. For example, let's say you have a function that looks now like this, and you go from let's say B now is here and A is here. So this is a relative maximum, this is a relative minimum, but now this will be the absolute maximum, and this will be the absolute minimum. So to find the absolute maximum or absolute minimum, not only you have to check the slope, but you also have to check the endpoints of the interval. And we'll get to that at the end of section 4.1. Now we have the following theorem, which is called the extreme value theorem. And here by extreme, it refers to maximum and minimum. And the theorem is straightforward. It says that if f is a continuous function on A to B, then f of x attains or it reaches the maximum and minimum, which is kind of obvious. So this is what I mean. You have a continuous function from A to B. If the function is continuous, it has to have a maximum, and it has to have a minimum. In this case, it's actually referring to the absolute maximum and absolute minimum. So that should be obvious. Okay, doesn't matter which function you have, as long as it's continuous. And let's say now a is here and b is here. If the function does this, clearly this is the max, and this will be the minimum. So the extreme value theorem only does, it guarantees that there is a maximum and a minimum if the function is continuous, which should be obvious. Before we start solving some problems, we need two more very important definitions. The first one is called a critical point, and you're gonna be listening to this probably thousands of times. So what is a critical point? So f of x has a critical point at x equals to c if f prime of c is equals to 0 or f prime of c doesn't exist. Okay, so this is very important. And here x or c in this case must, so this is very, very important, must be part of the domain, which again, it should be obvious, but many people miss this part. Okay, so therefore you look to the previous two graphs. This is a critical point because the derivative here is 0. This is also a critical point. So usually the minimum and maximum are going to happen at critical points. Now there is also something called Fermat's theorem, which is completely related to this, and it says the following: if f has a local maximum or minimum at x equals to c, and if f prime of c exists, then f prime of c must be 0, which is kind of the opposite of this right here. Hence, what these two things are really saying is if you have a critical point, then the derivative must be 0 at that point, or it must not exist as long as this is part of the domain. Or you have a minimum or maximum and this exists, then the derivative has to be 0. So the main idea in this section is going to be on getting the derivative equals to 0, so you can get the critical points. And if it's a critical point, it will be either a relative maximum or relative minimum. We will explore that more later, but you can see if it changes from positive slope to negative, clearly it's a maximum. And if it changes from negative slope to positive slope, it will be a minimum. In section 4.1, the main concern is how to find critical points, which should be obvious based on what we've done before, because all you do is you take the derivative and set it equals to 0, like you will see in the next page. Let's try a few examples before we do the derivative and try to find the critical points for f of x. Let's do g of x first. So what will be g prime here? Well, g prime is going to be 6x squared minus 6x minus 72. And remember, what we want is g prime equals to 0. That's what critical points means. Okay, so from here, usually this involves factoring. So you can factor the 6. This is x squared minus x minus 12. You want this to be 0. So this will be x minus, or x plus 3, x minus 4 equals to 0. So therefore the critical points are -3 and 4. So these are the two critical points. I'll just call it CP from now on. All right, so now let's try f of x. Here f prime is equals to 6x plus 2x plus 2. If we want to find the derivative equals to 0, that means the 6x squared plus 2x plus 2 is equals to 0. Then factor the 2, so it will be 3x squared plus x plus 1 equals to 0. Notice that you cannot really factor this, so therefore your other choice is going to be to use the quadratic equation, which will be -1 plus or minus, and this will be 1 squared minus 4ac. But notice that this part is going to be negative, so therefore this has no real solution. So this question has no critical points, or this function has no critical point. What that means is that the function is always increasing, so there is no point where the derivative will be 0. That's all it means. All right, what about the next one? This one, when you take the derivative, you have to use the product rule. So here f prime is the derivative of the first one, which is minus 2 x to the -3 times the second one plus the derivative of the second one, which is 1 over x times the second one. So you did this before in 3 point something. Before we set it equals to 0, notice this. This is very useful to make the factoring pretty simple. Notice that if you multiply this, you end up with exactly x to the -3. So therefore, if you factor x to the -3, this will be equals to -2 ln x plus 1, which is equals to -2 ln x plus 1 over x cubed. Now for the critical points, which is what we want, remember critical point means that either f prime is equals to 0 or f prime does not exist. So first let's go where this is equals to 0. So to be 0, you only focus on the top. So f prime equals to 0 means that -2 ln x plus 1 has to be 0, or ln x has to be equals to 1/2, or x has to be e to the 1/2. So that's the critical point. Now f prime does not exist when x is equals to 0, because we cannot divide by 0. However, x equals to 0 is not part of the domain. So since this is not part of the domain, this cannot actually make a note in a different color, because this is very important. So x equals to 0 can not be a critical point since x is not part of the domain. If it was part of the domain, then x equals to 0 would also will be a critical point. Okay, so this is very, very important, this note in red. Now, question 48 is asking you to find the absolute maximum and absolute minimum. So for this, you have to check, first you need to find the critical points, and then you have to check the endpoints, because it's asking for absolute maximum or minimum. Remember that critical points, all you do is you check here and here, or you find these values. But if it is a closed interval, you also have to check the endpoints to see which one is the absolute maximum or the absolute minimum. So let's start with the critical points. Remember, critical points first, the derivative The derivative of phi is 0, then this is 54 minus 6x squared. Therefore, f prime equals to 0 means that 54 is equals to 6x squared, or the x squared is equals to 9, or the x is equals to plus or minus 3. But since we are only going from 0 to 4, that means the only critical point here will be x equals to 3. So let's see what is the value of f of 3. So f of 3, which remember this is the critical point, this is phi plus 54 times 3 minus 2 times 3 q, which is, this is equals to 113. We should check that ourselves. All right, so now let's look to the n points, and this is referring to the x points of the interval, which in this case are 0 and 4. So what happens if x is 0? There is no calculus here. This is just substituting into the function. F of 0 is equals to 5 plus 0 minus 0, which is just 5. And the other endpoint is x equals to 4. So how much is f of 4? So this will be 5 plus 54 times 4 minus 2 times 4q. And this equals to 93. So clearly this is the biggest one, or the biggest one. So this will be the max, or this is the absolute max. This is the smallest one, so this is the absolute minimum. And 93 is just the end. So what happens in this graph, it means the graph looks something like this. You go from 0 to 4. This is not a precise graph. This is just giving an idea of what's going on. Then one of the critical points is 3. The biggest value is going to be 113, which will be somewhere here. Then when it gets to 4, this is equals to 93. And the smallest one is 5. So the graph does something like this. All right, so that's it for section 4.1. Again, to recap, the main idea of this section is you have a continuous function. If the interval is closed, you will get a maximum, an absolute maximum, and an absolute minimum. If the interval is not closed, it's open, which means it can go from minus infinity to infinity. Then where the derivative is 0 will be either a relative maximum, which is the case, or a relative minimum, which is also called local maximum or local minimum. So all you do is just find the derivative, set it equals to 0. That will give you the critical points, which means there's a possibility that that is a maximum or a minimum there. All right. Now let's go to section 4.2, which is called Rolle's theorem. So this section looks a little technical, but that's just because it's new. But this is technically self-explanatory, like you will see right now. So you have two main theorems, or three, but two are the main ones. Rolle's theorem says the following: if f is continuous between a and b, okay, and differentiable, remember differentiable just means that the derivative exists. So let's say you have a is here and b is here. So the function has to be continuous from here to here. The derivative has to exist. And this is very important. F of a has to be equals to f of b. So for example, let's say that this is f of a and this is f of b. So the function could technically do this, or it could do this, or it could just do this, it could do this. It doesn't matter. It just has to start in f of a, and f of a has to be the same. So if that's the case, so if you have one function that satisfies that, okay, that f of a is equals to f of b. So let's say here's a and b, and let's go with the most simplistic one, which is this. So that means that there is a c between a and b where the derivative is 0. So all this is saying is that you start at this point and you end at that point, somewhere in between A and B, the slope has to be 0. That's all it means. At least once. Like for example here, this will be the value C, and it can also be here. So that's all it means. Okay. So for example, we have this function here. This is a polynomial, so clearly this is continuous. So remember, CTS means continuous, so that checks. Now, is differentiable? Yes, because you can find the derivative of this one easily, or the derivative clearly exists between -2 and 2. And well, here's the derivative, just to show you that. The derivative is 3x squared minus 4x minus 4. So clearly the derivative exists. Now the last thing you have to check, which is the tricky one, is f of -2 equals to f of 2. Well, let's see. And you should check this by yourselves. F of -2 is actually equals to -6. And f of 2 is equals to -6. So therefore, this condition also checks. So therefore, what this means is that there exists, according to a Rolle's term, a value of C, okay, between -2 and 2, such that f prime is equals to 0. So this guarantees that there is a value where the derivative has to be 0. Now, in this case, you want to find this value, you're going to have to use the quadratic formula. Well, not necessarily, but that will be the easiest way. So here x will be 4 plus or minus 16 minus 4 times 3 times -4, everything divided by 2a. And when you simplify, this is 4 plus or minus 8 divided by 6. So that means that x is equals to 2 and -2/3. So as you can see, there are two values of C where this is the case, just as promised by the theorem. And that's it. The next theorem is actually very interesting because this is a connection between algebra and calculus, like an official connection. And this is what I mean by that. If you have a function that is continuous, just like Rolle's theorem, and also differentiable, just like Rolle's theorem. So these two conditions are the same. This one doesn't require that f of a be equals to f of b. So what this says is if you have a function that is continuous between a and b, so let's say a is here and b is here, and then you have a function that is continuous between here and here, okay? Then there exists a c between a and b, where the slope of the function, this is the slope of the official function, this is the line, where the slope is identical to that. So for example, the c could be here. Notice that this slope is identical to this one. So that's all it means. Or in other words, is saying there is specifically one point only between a and b where the algebra slope, okay, so you can think of this as the algebra slope is equal to the calculus slope. Okay. All right. So let's see how this one works. So we have the following function, and you go from -2 to 2. So is this continuous? Yes, because it's a polynomial, it has no issues. Is this differentiable? Yes, because you can take the derivative easily. In fact, f prime is 3x squared minus 3. So you can see that's very simple. Here the value for a is -2, the value for b is 2. So what the intermediate value theorem is telling you is this, that there is a value where the derivative should be equal to the slope. So first let's find the actual slope. How much is f of -2? And you should check this value. This is 0 and f of 2 is 4. So therefore the algebra slope, which is technically f of 2 minus f of -2 over 2 minus -2, this will be 4 minus 0 over 4, which is equals to 1. So according to the theorem says the following. So therefore, by the mean value theorem, there exists, so this is the fancy way of saying there exists mathematically, there exists a value of c between minus 2 and 2, such that f prime of c has to equals to 1. Now we already know what f prime is, so all we had to do is set it equals to 1. So that means 3x squared minus 3 has to be 1, or 3x squared has to be equals to 4, or x has to be plus or minus the square root of 4 over 3, which just equals to plus or minus 2 over radical 3. So these are the two values. In this case, c1 will be 2 over radical 3, and c2 will be minus 2 over radical 3. So you can have more than one value that satisfies the theorem. Now the next few problems we're going to do, they look a little more technical. And by technical, it means you have to prove some things, but they all rely on either Rolle's theorem or the mean value theorem. The first two, they rely on Rolle's theorem, and technically we're going to prove the solution by contradiction, and this is what I mean. So here we have the following function. F of x is equals to x cubed plus e to the x. And you want to show that it has exactly one solution. Okay. So first, we need to show that this actually has a solution, and this is just algebra. So first, show that there is at least one solution, and then we'll show that it's not possible to have two using Rolle's theorem. So how do we show there is actually a solution? Now, since this doesn't give an interval, you can pick an interval. So let's say we focus on the interval from minus 1 to 0, okay? Then you'll see that it's not that it doesn't matter which interval you pick. Well, it does matter, but you have flexibility. So how much is f of 0? Well, f of 0 is 0 cubed plus e to the 0, which is just 1. The point is that this number is positive. Then how much is f of negative 1? This will be negative 1 cubed plus e to the negative 1. All you care is that this number is negative. So here you have a function that it changes from positive to negative. So clearly there is it crosses the x-axis at some point. So there is at least one solution, because it's possible that also could do this. In this case, it will be two solutions, and we'll show that that's not. We're going to show that's not possible. So therefore, for now, by the intermediate value theorem, which we talked about this theorem before, there exists at least one solution between, let's just call the solution C, between negative 1 and 0, okay? So that's what we show so far. Okay, so now let's use Rolle's theorem and show that it's not possible to have two solutions, okay? So now let's assume, so this is a big assumption, and we're going to show that this is not possible, that there exists two distinct solutions, okay? So we assume that you can find two solutions, or two roots to the problem, okay? So therefore that means that you have A and B such that f of A has to be 0 and f of B has to be 0, okay? Now by Rolle's theorem, which is the first one from this section, that implies that there exists a C a C value between A and B such that the derivative is equals to 0. So that's what it means. Now this is a part that is tricky, so you're sleeping, this is the best time to wake up. But, and this is going to be the contradiction, f prime is equals to 3x squared plus e to the x, which is always more than 0. But the theorem says there has to be a value where this is equals to 0. So therefore this is a contradiction. So this implies that this is a contradicts Rolle's theorem. Okay. So that implies that you cannot, or that you cannot have two solutions. So you cannot have two solutions, but we already show that you can have at least one based on this, which is this part. So that implies that you have exactly one solution. That's it. So look over this, and we'll go probably over this question again in class, but give it a try a couple times. Then you can ask this in class for sure. Right, now number 22 is saying show that this one has at most two roots. This one is not saying exactly, so you don't have to show that they exist. You just have to show that at the most you can have two. So we're going to do the same idea. So we're going to assume that there exists 3 roots, and we're going to show that that's not possible. Okay, so if there is 3 roots, that means that f of a has to be equals to f of b, has to be equals to f of c, has to be equals to 0, where a is less than b is less than c. Okay, so therefore by Rolle's theorem, so we're going to use Rolle's theorem twice. But Rolle's theorem, there exists, let's say, R between A and B such that f prime of R is equals to 0. And then by Rolle's theorem, there exists, let's say, a T between B and C, okay, such that f prime of T is equals to 0. But here we have that the derivative f prime is equals to 4x cubed plus 4, okay? And c is a constant. That was probably not the best choice. Let's say that this was k. Doesn't matter, the derivative will be 0. So f prime equals to 0 means that you have 4x cubed, or you can factor the 4, times x plus 1 will be 0. So now if you factor this is x plus 1, and this is x squared minus x plus 1 if you follow the factoring formulas from algebra. So notice that this is equals to 0 only when x is equals to -1. But according to this, there has to be 2 values, r and t. So, okay, we can say that this is equals to r, but what about t? So t doesn't exist. So therefore, this is contradicting the theorem, just like here. So you technically say the exact same thing you did in the other one. So that implies that f prime of x equals to 0 has only one solution, not 2. Okay. So therefore, that implies that you cannot have 3 roots. So that implies that at most you can have 2. Okay. All right, so now let's do one where we use the mean value theorem. Here, let's say that f of x equals to sine of x. Okay. So by the mean value theorem, that implies that there exists a value, or there exists c between a and b such that f prime of c is equals to f of b minus f of a over b minus a, right? That's what it means. In our case, that means that you have sine of v minus sine of a divided by b minus a. So now if we cross multiply, we get that sine of v minus sine of a is equals to f prime of c times b minus a. So now if we take the absolute value, so this implies that the absolute value of sine of v minus sine of a is less than or equals to, or actually is equals to the absolute value of f prime times b minus a. Now the key to this problem is the following. F prime is going to be cosine x. And remember, the biggest that cosine can be is 1, and the smallest it can be is negative 1. So that implies that the absolute value of, doesn't matter which value this is always less than or equals to 1. Therefore, from here, it follows that this is less than or equals to 1 times b minus a. And that proves this, which is a classic problem that you will keep seeing in calculus 2, calculus 3, and so forth. All right, finally, this one is very interesting problem, and you're going to use the mean value theorem to show that this is not the case. So here it says that a fixed point is something that satisfies this if f of a is just equals to a. So it says that if f prime is not equals to 1, show that you have at the most one fixed point. So we're going to do contradiction again and assume that f of x has, let's say, 2 fixed points, okay, and which would be different, a less than b. So that implies that f of b is equals to b and f of a is equals to a. That's what it means to be a fixed point. So therefore, by the mean value theorem, there exists a function that exists. So by the mean value theorem, there exists a c between a and b, such that the derivative will be equals to f of b minus f of a over b minus a. So in this case, since these are fixed points, that means this is b and this is a, and this is b and this is a, which is exactly 1. So if you have 2 fixed points, that means the derivative has to always be equals to 1. But this is saying by assumption that it cannot be 1. So therefore this is a contradiction again. So that implies that you have at most 1 fixed point. And that's it.